This is supposed to be working now. Yes. So, I want to just vomit of what I have been studying from yesterday. It well, converting the equations of fluid dynamics into geometric analysis and smooth manifolds notation is not easy because the main problem is with time dependent vector fields and worrying about them. So I clarified myself with what time dependent flows are actually like. They, from Lee again. I keep getting back to it whenever I need the time dependent flows. Anyways, so what the main crux of the matter is, uh, how does really vorticity flow? Vorticity is what stays frozen in when the fluid is flowing. What does that supposed to mean? That is supposed to be Helmholtz theorem, at least one of the three statements of the theorem on vorticity, at least two of them, at least anyway. It states that vorticity is will stay zero if it's initially zero, and it will state non-zero. It will stay exactly the same amount. Okay. Anyways, um, so what is it? So this is from a book. This is an anthology book written by multiple people, and this article is on geometric aspects, really topological aspects. Are later on this same section. Now, velocity field is the curl of the velocity field. It depends on time because v depends on time. Curl of v is double omega. I don't really like this notation. Omega should be the form. When I'm saying vorticity field, I will use W, and that's supposed to be curl of V, and it flows in this way if V satisfies this equation. Everyone uses U. I don't like U. V, and we'll use V, and then it will flow like this, which is determined from the Euler's equations. That is fine. Now what they're trying to say is we can classify local invariants which are dependent on the metric. Yes, they are dependent. I mean, they are not really dependent on the metric. Eventually, I don't know. Doesn't matter. Point is, there should be four types of matrix invariants, local invariants. So we should be able to initially specify them. Initially, at time t is equal to zero, and then we should be able to say that it's staying conserved. Their integral should be conserved, something like that. Key, we should be able to say. They are locally conserved. They are flowing in a way. They are not just jumping non-continuously and staying invariant through time. Whatever that means. Okay, now there are four types. The four types are of they're ordered in this way. I don't like this order because eventually you will see the four types can be ordered in a very nice way and classified in a nice way, which is what this statement is saying. To classify, the problem is to classify relate ideal fluid invariants. These are all ideal fluid invariants. There is no viscosity anywhere. You can define all this in viscous flows also, but it will not be invariant, I think, anyway. um, their natural setting in the language of differential forms. So there are four types. Four types are, for example, mass density, mass per unit volume. That satisfies the conservation law. How does the conservation law work? It looks like this, but if you initially integrate, so so it depends on the Reynolds transport theorem. It says, I don't know if I have done this calculation. I will explain the calculation here, but the point of the Reynolds transport theorem is if you integrate, so you fix a initial area, initial set, which is my gamma, capital gamma. I set my initially, then I will flow. Eventually, I will become phi eventually it will map to phi of t of gamma, which means that it will, and it starts with times t is equal to 0. Time t is equal to 0, phi of 0 is identity. So initially it was gamma, double gamma, and then after time t is equal to t is phi of t of gamma. And now then I integrate any function g, smooth function g, on phi of t of gamma. That's what I'm integrating on. So that integral I can do, but again I'm integrating a smooth function, so it's a bad way to see things. I should be always integrating differential n forms if I'm integrating over an area. Okay, I didn't mention here. Okay, this calculation only depends on. This calculation is only for n forms when I'm doing in Rn, but this next equation, this is the geometric equation. This works for any form, and b can be anything. That's why I wrote a different symbol B here in the downstairs, but I didn't know why. Now I get, because I have this idea. Anyway, that was a different reason. Anyway, so I integrate G, and in phi of t of gamma, I'm integrating G over this volume form. How do I do the integral? I need to change coordinates. I am assuming phi of t is nice enough so that I can change coordinates, and then the coefficient that comes out is determinant of Jacobian of phi of t, which is a time dependent real number because it's a determinant of a matrix, so it's fine. I'm multiplying this real number with another real number and I'm integrating over y. Y is my initial area, so I can integrate there. Now I take time derivative of these guys. The time derivative goes inside and then it takes a derivative. I don't know if this should be partial or total derivative, it doesn't really matter. It did the calculation, I'm not sure. The answer is supposed to, this answer is right. This I wrote down by the statement of the theorem, but I don't know how. It straightforwardly comes out, I guess. These two terms will combine to become this divergence term. Now, d phi dt is supposed to be a vector field at time t. Yes. That is how we have in fluid dynamics we have the vector field, and then we compute. We don't really compute. We say that flow exists, time dependent flow, and so phi of t is supposed to be the velocity of how fast the fluid is moving. That is what the state say when they state the theorem, Reynolds transpose theorem, and so this integral is supposed to be this integral, and if this integral is 0, then if I integrate over initially time t is equal to 0, it will be same as any time in the future. So that is what this equation tells, that rho, initially if I integrate over an area, then if I let it flow, that after time t, that area will have the same rho integral. Okay, that is what they're trying to say. Now, there is a conserved quantity of type 1. Type 2 is, I put ink, so it's just one dot and let it flow. Then that sign variant, because I need a better example than ink. It's called a Lagrangian invariant. The equation it satisfies is this. It looks very similar to the not the previous one. It looks very different from the previous one. Another third type. Second type I need more examples, but the third type is more interesting. Its example is vorticity. Vorticity satisfies the equation like this. Vorticity vector field will satisfy equation like this, which I denote by W, not omega. Okay. What will happen there is, if I integrate the vorticity initially, is that supposed to be it? So I am working under the idea that this is so what they are saying is all of these equations, there is fourth type of invariant which satisfies this equation, which is also a vector, they are all coming from Lie derivative of differential forms. So if you differential 0, 1, 2, 3 forms in a 3 manifold will give you this Oh, okay. They have a nice notation for it. Anyway, so this is the usual Lie derivative for the vector field u at time t. They're not mentioning the time t, but it's there. This whole thing is dependent on time, and they're saying it's zero. It adds up to zero at all times. Anyway, what they're saying now is all of these are equivalent to this equation. How do I convert from this to there? You need to define, so this scalar quantity is a zero form, obviously. This conserved quantity rho, you have to multiply with the volume form to make it a, so because rho is naturally a volume form, it's a three form. That's why we can integrate it over three-dimensional subspaces and get mass as a numerical quantity. That is supposed to be the three form. The two form is supposed to be vorticity, frozen in vector fields, and the no, yeah, that is the two form, and the one form is supposed to be this kind of invariant. I have never seen an example. I will study momentum of a vortex ring later on. Then I will see how that travels. It should be traveling. So, in this equation just means I'm assuming what I have written here is correct. So the Lie derivative, this should be the total Lie derivative, and I have distributed them into the time derivative plus the not the time derivative. And this upper equation should be looking similar to this equation if I know the Lie derivative of differential three form is the divergence times that form itself. So yeah, that is a very nice way to think about divergence. It is measuring how on the flow the three form changes. Now, mhm. Now if this equation is correct, then what it is saying is if I choose any p-dimensional, it's called a chain. It's like you can choose a area, volume, or line, or a dot, and integrate initially. That so initially at time t, very t, and I take the time derivative at t, then that would be equal to this right hand side. So if the right hand side is zero, then which is supposed to be zero for these invariants. This is what they are trying to say. These all invariants are supposed to be having the right hand side to be zero. Then the integral is zero at all times. That is one way to state what the invariant is supposed to be. The invariant is the I give you a differential k form, and the invariant is you initially whatever the integral is, it will stay there. If I let it flow, and I can let flow any kind of sets like a dot, a line, a area, a volume. These are four kinds of B that can be. Okay, fine. But I should be able to think of. So, what does the frozen in criteria mean? So, so if it's this integral idea is same for all of these invariants, but this frozen in idea. So this is the list, and yeah, this frozen in idea should be only specific to the two form. I should be able to say something about the frozen in terms of Lie derivative or something. I don't know. That is one of the things I want to work on. The main thing I will try to figure out is what is the Lorentz transpose theorem. Lorentz transpose theorem, I think, just states this. That is what it's supposed to be, because it's just saying there's some that's the third term which is coming from the Jacobian. That is what is giving us this. And yeah. So what else? Yeah, so this is a nice unification in terms of differential forms. And oh yeah, so okay, I got it. So the frozen in idea, I think, should be what the statement of Helmholtz theorems are. Helmholtz theorems state that this is all inviscid flows. So ideal flow with, I think you need to assume more, like there is no, I don't know, isentropic flow or something like that. Anyway, so they are stating that the strength is constant. This is the integral idea. So we need to, so vortex line. So how they are different? What is a vortex line? So that definition are here. So what I can start with, so mass density is a differential 3 n form, n equals to 3 in all of the cases here. So yeah, this is a differential 3 form. I can integrate over volume and then get the mass in that volume. Velocity is a vector field, but I can change it to a one form by using the metric. I am on a Riemannian 3 manifold. I have to do fluid dynamics. I need more structure than a smooth manifold. I need a metric also, and that gives me a form. I could choose a volume form in a different way also, but doesn't matter. I'm choosing the metric volume form. That should be fine. Metric volume, not choosing the metric volume form actually has the purposes. You can prove that something is not metric dependent and just volume preserving dependent. Anyways, that is what the Arnold's book does. Now this one form, I can take its extended derivative and gives me a 2 form, and that is supposed to be the vorticity 2 form. And I could easily take the curl of this V, which would look like and W and omega would be that would be W, and omega would be d of the one form, which is coming from the velocity, and they are related by this. They are related by, if I take the volume form and I product that with the vorticity vector field, I would get a vorticity 2 form. Yeah, it's a mess. Anyways, these two satisfy equations of this form, which are weird looking, yes. Now, this equation is a nice, easy equation. This is just saying that it's conserved in this sense. This is the unification conservation law, that any k form, if it satisfies this equation, they are conserved. I have written V here because, of course, V is dependent on time. There is no time dependence written explicitly, but everything depends on time in general. What are vortex lines? Vortex lines are not this. Vortex lines are flow lines of W. Because W is dependent on time, I can't write exponential or vector field. That won't work. These are the vortex lines, really. Vortex, I don't know. So Helmholtz theorem states that vortex lines can't be just lines. They have to be either circles, or they have to end somewhere on the boundary of the domain. That theorem is also, I think that is provable easily. So the statement, the intuitive idea is divergence zero implies something about the flow lines. That just you have to say a right statement, because you can't just say the flow lines would be. So intuition comes from magnetic field. Magnetic field always form loops because magnetic field divergence is zero. But it will never start anywhere. If it starts some point, then divergence is not zero around that point. You can integrate around. So it should be, there should be no start and no end. That's how magnetic vector field lines work. And this initially irrotational remain irrotational, and initially so vorticity 0 means it's irrotational. Vorticity non-zero means it's rotational. It measures rotation in some way. Vorticity vector field, I mean, we can interchange between them. Are they related by? No, they are not. The 2 form we can convert to a vector field in a different way than how we convert 1 form to a vector field. That relationship. So I can the integral of the 2 form would be equivalent to the surface integral of the vector field, not the line integral. That is what the geometric background is. That's why there's these 2 columns, and 2 columns are important here to understand the whole thing. And yes, at least for me, I'm on the one who's understanding here. Um, I guess I'm trying to understand. So it will be my way of understanding it. Fluid element is initially. So what we need to show is that initially, okay, let's just not worry about these things. So initially, if there is a I don't know how we could do that. That makes no sense. Yeah. So I try to do it here. We have to define the flow. What is the flow line somehow, and then yeah, I will have to try that. But that is what the frozen in criteria really is. It's different from this integral criteria, which is what strength of a vortex line is this. So I should continue following this table. What is direction is just a vortex flow line direction. That's fine. I could have a vortex tube, which is a whole three manifold full of vortex. What is this? So yeah, it should satisfy a tangential criteria. It should be tangent to the vortex. So these vortex tubes will flow in a very invariant way. So it will flow. So they will never mix. So Helmholtz theorem, I am picturing it in this way. Ideal fluids never allow mixing of this irrotational and rotational pieces, which are initially these are these pieces, and then they will flow in that way. They will never mix initially. So if I start with the flow lines of V, I will never start from a rotational piece and then go to a. I will never gain rotation. That is the same. So there is no dissipation. That is a dissipation is statement about energy. I think energy is not conserved for Navier-Stokes equation. I'm not sure, but that mixing idea definitely depends on what is the viscosity. Um, Now, what they're trying to say is I can integrate this vorticity on. I have to integrate it on a two-dimensional surface. I can't integrate on a three-dimensional surface. So take a vortex tube and then take a cross section, and they can integrate, and it doesn't depend on the cross section. So that is what they're defining. That is fine. So this is a major idea behind vortex lines. And this is the piece I think I was missing from the intuition about what this is. So inviscid flows in the observation of real fluids, the strength of wall is always gradually decreases because dissipative effect of viscous forces. How is energy related to vorticity? That is a different question, I guess. I don't know if they are related, but there are a lot of examples. But this, yeah. Mhm. This is fine. This is already proved by that integral idea of d derivative. That is fine. Yeah, so we may try to cook up. I don't know what they're trying to do. This is another lecture of who is trying to prove this theorem. Proofs are so hard to find all of them, all these. I don't know. So this relationship is weird. I'm saying weird because what do we need to prove? I need to prove that this should be x here. So if I have a time dependent vector field x, then I have a time dependent flow. That is fine. This is my notation. This is my made up notation, which I made up yesterday. Then what I need to show is I have a W. This is a vorticity vector field. I am taking the flow of that from time t is equal to 0 to t, which I will write as t. That is fine. Now, So if I this is a time dependent one parameter from the diffeomorphisms local diffeomorphism. Okay. It will flow and this will define a line. What else will that do? Huh. Vortex tubes arbitrary integral is 0. Where was the proof again? Oh, it was in that book. Hang on. Hell. Hmm. Where is that? That book. Why am I not starting with that? What is it? Yes. Let's find over. Hmm. This book is supposed to be Cambridge monograph on mechanics and applied mathematics. So I'm assuming I can trust it on its okay, rigor. Yeah. Kelvin's evolution theorem and three laws of what is 10. What they are trying to do is do it component wise. 10. Okay, what they are trying to do is take the flow map of W and then check which theorem is Helmholtz law 1. First and second should be the proof. Hmm. They satisfy this type of equation. That is why they are doing it. Uh, I mean, this has nothing to do with the form. The statement is about that is the geometric understanding. There are two different things going on over here, and they should be so general. So they should be take any three manifold with a volume form. That should be that should not be enough. What you need is this. Yeah, you need a volume form. That's it, I guess. So take a volume form of a three manifold. You can convert two forms to vector fields, and that is isomorphism. And then if that vector field, okay, you need to do curl, you need a metric. Or do you? You need a metric. So on a 3D and C manifold, then if any vector field satisfies this kind of equation, where W is curl of U, then whatever is happening, that should work out. What they're trying to say is you flow. So yeah, this is a solution. So if you flow along U, so the velocity vector field U here, then uh, solution exists if initially u 0. If initially omega was 0, then this time derivative would be zero at all times. That makes sense. But if initially already a line, which means you're just choosing a set and then you are flowing through it, whatever this sentence means. Just converting this to the geometry language is what I'm trying to do. Yes. And the solution exists in terms of strength tensor. What? So that you're taking component and then each component will have this, because this is the gradient. I don't understand. I have written another equation probably wrong there, but what they're saying is the general equation is probably this. Tell them this. I don't know what they're trying to do. In any case, they take I can't do this because omega j. Oh, it's curled because that's why the omega j omega would be zero. And then they are saying that this shows that the rate of change of vorticity following a fluid flow is proportional to local change of strain tensor. It does not explicitly depend on the local vorticity or rotation tensor. Our local strength tensor is zero for what? Is that correct? This right hand side is zero, so it's zero anyway. The strain tensor for ideal fluids is zero. That is probably it. Huh. No, no, no. I don't steal for the argument. That is what I need to cook up on my own, I guess. So you need to be a flow line argument. If I flow through, then do a push forward. There should be a, I don't know, I need to take components, I guess. Yeah, that makes sense. What they're saying is a component idea, yes. That is what the lectures by that guy, this guy, lectures by Professor Renzo also mentioned that this is a component wise argument. So what they're doing is, yeah, that makes sense. So I have, this is a separate statement than the sugar of this. There should be separate statements. I don't know what for, what is still going on though. They have a unique solution for some time. That is what is up. Yeah. Okay. This book is a readable book, but again, I mean, the proofs are, there are a lot of stuff here. There's a idea that vortex lines and tubes would make sense. This makes so much sense. And so looks so nice. And I can only do this in RF, obviously, and locally on any three manifold, of course, but only locally. But the equation, just like it so much now. This proof is fine. No, I'm not talking about this one. I'm talking about this piece. They can define. This could be so good. Like on any Riemann and 3 manifold, I should be able to do this. Fine. I don't know how to. So it should be a pair. Yeah, the three form and a better field, but still this inertia tensor of the fluid particle is weird. Funny. Hmm. Yeah, so that's it. I'll cook that on my own. So there I give you the three types of invariants and how each of them are weird in their own ways. So this is frozen in, so that the vector field. So I can convert that two form into a vector field. But, and the statement is different from the area integral. We are saying about something about if I'm zero, I will go to zero. If I start with some number, I mean, I think there also things it will probably rotate or something. No, whatever that means. The the vortex piece and the non so okay, the vortex piece and the non-vortex piece they will stay separate, but internally they can mix. They're not like they will be rigidly moving. Or is that what they are saying? It's not explicitly on local velocity or velocity vector will not change the body deformation since the vortex length rotates it. Omega and constituents. Okay. Anyways, I don't know if that statement is even possible to write in R3 manifold and only possible to write it in R3 or something. But I mean, it should not be metric dependent, that statement. Anyways, conserved quantities are fine. There is no vector field associated to it, but there is a vector field associated to it, which is the I don't know what happens to this one for Venus invariants. Cool. That's it for